Melissa Davis, and I'm the project manager for my senior design group. We did a portable OLED panel system. Unfortunately, Dr. Cook is not able to be here today, but here's my main advisor. Like I said, my name is Melissa Davis. My partners are Sabhar Abu Sharak, Sherry Trevu, and Brian Mansell. Our secondary advisor was Dr. Lori. So we begin with a short introduction of what an OLED actually is. So an OLED is a lot like an LED in the fact that you apply electricity and you get illumination. However, OLEDs are made out of organic materials such as carbon. And in addition, when you have an LED, you have an entire little point source that's illuminating, whereas an OLED, you can have an entire surface illuminating. Currently, OLEDs are being used, but they're pretty high cost and are pretty expensive. So they're mostly being used in high-cost applications such as TVs. And if anyone has a Samsung Galaxy phone, S7, you have an OLED. Congrats. So there's some very unique advantages of an OLED. One of the first ones is the fact that these are very, very light. They're as thin. There's probably as thin as a paper. In addition, the substrate that you can manufacture it on can be made to be flexible and transparent. I think one of my favorite advantages is the fact that when you illuminate it, it's a soft diffuse light, and it's very close to natural light compared to the harsh light of fluorescent. And one of the most important factors is OLEDs require a lower driving voltage and are more efficient than LEDs. So we had a sponsor for our project. Our sponsor was Corporate Technologies, and our sponsor gave us a task to create a portable OLED panel system. He has a patent for OLEDs for portable use and wear, and his vision for this product was to use a flexible OLED and attach it to the back of a runner or a biker so they can be seen at night. Unfortunately, flexible LEDs are a very high cost and aren't market ready, so we stuck with a rigid LED, which is lower cost. The thought of this one is that it can be handheld since it is light, and it also, when you go camping, since it's a diffused light, you can attach it to the top of your tent, and it will illuminate the entire tent. So since we were given a sponsor project, we didn't have too much wiggle room. We had some very strict requirements. The first requirement was that our entire prototype needed to be as lightweight as possible. So since this is going to be used in camping, we don't want to burden the user. Our goal was to have this 50 grams or less. In addition, we want a rechargeable battery so that a user can recharge it instead of having to carry batteries when they go camping. In addition, our prototype must illuminate for 3 hours. And I think our most difficult challenge is the fact that the entire project needed to be $25 or less so that it could be marketable. And to put this into context, the OLED panel itself is $25. And then once you add in the battery and everything else, we had very, very little amount of money to actually spend stuff. But we were able to add additional features, such as the ability to blink the OLED, and we added LED lights to let the user know if the battery was low, if it was charging, and if it was done charging. So beginning last semester, we were looking for a power supply for our device. In order for it to be lightweight, low cost, and be able to last long enough, we end up using a lithium-ion battery. And the lithium-ion batteries in our budget that fit our specifications are lower voltage, so 3.7 volts, which is a minor issue because in order to illuminate the LED, you need between 8 and 9 volts. So we used a boost circuit to set the voltage. In addition, since we selected a lithium-ion battery, there's additional safety concerns to have. First of all, we don't want the user opening up the panel and taking out the lithium-ion battery because if it's punctured or bent, then it could be a little dangerous and explosive. So what we did was we wanted to make sure that the user would just plug in and charge it like your phone. So a USB input would be 5 volts, and with our battery at 3.7 volts, we needed to step it down to protect the battery. In addition, we added this circuit with the charge controlling circuit that would allow the charge going into the battery to never go above 500 milliamps. Because, like you guys know, with lithium-ion batteries, if it gets too hot or if you overcharge it, it'll damage it, and it may possibly explode.
For this project, we decided to use a microcontroller for 2 functions. One, to monitor the battery and to let the user know the state of the battery, if it's a low voltage, fully charged, or if it's in a charging state. And the other function is to have some control over the OLED itself, blinking on and off. So we needed a microcontroller that could have a low operating voltage, had to have a built-in digital or analog to digital converter for monitoring the battery, had to have enough inputs and outputs for our system, and had to be inexpensive, and we decided on the PIC 12 F1501. This is the functional architecture of the system. Starting on the left, we have a micro USB input. That is where you would connect a charger. It is connected to the microcontroller and the charge regulating circuit. The charge regulating circuit is used to condition the power to be used to charge the battery safely. The battery provides power for the microcontroller and the boost converter. The microcontroller has a connection to the USB input. That is what is used to check if it's being charged, if the battery is being charged. It has a connection to the LED indicators, which are used for letting the user know if the battery is low, if it's being charged, or if it's fully charged. Microcontroller is also connected to a push button switch for turning it on, off, or blinking. And it also has an enable for the boost converter, which basically just turns it on or off, in effect turning the OLED on or off. And the boost converter itself takes the output voltage of the battery, boosts it to a higher DC voltage that can be used to turn on the OLED. This is the flowchart for the microcontroller, starting at the start up top. The microcontroller is always checking to see if the battery is being charged. If it is being charged, the microcontroller will check the battery voltage and check to see what level it is. If the battery is fully charged, a green LED will turn on, letting the user know that the battery is fully charged and you can unplug it. And then it'll go back to start and it'll do this again. If it's not fully charged, a blue LED will turn on, letting the user know that it's charging and needs to be charged, and then it'll go back to the start. If the microcontroller can see that it's not being charged, the battery is not being charged, it'll check to see if the battery is low, low voltage. If the battery is low, the red LED will turn on, letting the user know that the battery needs to be charged, and then we'll wait for the button press. If it's not the low voltage, the red LED will not turn on. The microcontroller waits for a button press. After the first button press, the OLED turns on. After the second button press, the OLED blinks. After the third button press, the microcontroller goes into low power sleep mode. Here's a video demonstrating the LED indicators. The first one is the red low voltage indicator. You can see the OLED is blinking in the background. Here we have a 3.1 volt, which is our minimum voltage, and we'll turn the voltage up, and this red LED will turn off. And you can see the OLED blinking on the side here. All right, it's turned off. Then the next one will be the charging. In just a second, the blue light is telling the user that the battery is charging and it's not fully charged. The voltage on the right is the charging voltage, and the voltage on the left, the 3.5 volts, represents the battery voltage. As the battery voltage gets turned up, the green LED will turn, or the blue LED turns to green, letting the user know that the battery is fully charged.
Okay, so after we designed all those circuits, we wanted to make sure that they were functioning properly and they met the requirements that the sponsor asked us to have. So the first thing to do was test the battery to make sure it did illuminate the OLED panel for at least 3 hours. In order to do these tests, I went ahead and I charged the battery up to its full capacity with 4.2 volts. I attached it to the boost circuit and then I attached the OLED and I counted it to see how long it would take the battery to die. There's no dimming with this because the boost circuit regulates it at a constant current and voltage, so it's on and then it just turns off. And the test showed that near full charge, the battery can provide an average of 4.5 hours of constant power to the OLED, which is more than enough for the requirements we were asked to meet. Okay, the next round of testing proved to be a little bit more complicated. We designed the charge regulating circuit in order to protect the battery. But as we did the tests with using 100 milliamp charging current, we noticed that it took 5 hours to charge the battery to its full capacity, and we're only getting 4.5 hours of duration out of that, so we wanted to see if this could be improved somehow. Looking at our circuit and the battery, the only variable that we could change was increasing the charging current to 500 milliamps. You would think that this would make it charge in 1 hour if you use the regular charging time equation. However, we quickly discovered lithium-ion batteries have nonlinear charging characteristics, so increasing the charging current doesn't really make it charge. It still takes it about 5 hours to charge to full capacity. However, increasing the charging current does let it shoot up to the constant voltage mode more quickly, so it gets closer to the full capacity of 4.2 volts. And this gave us about 30 minutes more of duration per charge time. And this is just showing you that as the battery is charging, it starts at 500 milliamps, but it quickly starts to decrease because the circuit's regulating the current so it doesn't harm the battery. And it gets close to 4.2 volts, but it doesn't quite hit it. The final test that we wanted to do was light intensity testing. During all the duration, it looked like it wasn't dimming at all, but we just wanted to measure this to prove it. So I went ahead and I measured the lux 12 inches above the panel during one of the battery durations. During the first half, you can see there's really not much dimming, but during the second half, it starts to dim by about 16%, even though you can't really see this just by looking at it. And if you want a comparison for the brightness on the panel, I measured a Samsung phone the same way, and it's 13 lux at full brightness. Whereas an LED light bulb in your house is 650. So it's a nice in-between.
So these are the user-friendly features on the end product. You have the LED indicator for the battery status. You have the push button to have the stagnant light, the blinking light, or off. And you have the charging port to charge the product. So this is how the inside looks like. You have the PCB, which includes the microcontroller, the boost circuit, and the charging circuit. You have the charging port, the lithium-ion battery, and the OLED panel. On the opposite side, you have the button and the LED indicator. So this is a video that just shows how the product works. So it's off right now, and on the first press, you have the stagnant light. And on the second press, you have the blinking light. And then on the third press, it just turns off, or goes into sleep mode. So over the course of the past 2 semesters, the products, or the components that we used in all cost about $250, and the total man-hours spent were about 900. So some lessons that we learned were that lithium-ion batteries have pretty interesting characteristics, as Sherry mentioned, and that PCBs can be pretty temperamental. The copper wire likes to pop out a lot. And OLEDs can be pretty fragile. They're easy to break, and microcontroller selection is key. So the cost of our prototype is approximately $30, which exceeds the $25. But when this is produced at mass production, it goes down to $22.50, which is lower than the $25 that we're requiring. So in summary, our total final product, the specification required $25, and the end result, we got it to be done at production quantity at $22.50. The weight is 50 grams was the specification. Unfortunately, we didn't meet the weight requirement. Our weight is 85 grams. And the duration for the battery is exceeded. We wanted it to be at 3 hours, or the sponsor wanted it at 3 hours, and we got it at 4.5 hours, and it was rechargeable. And we also added the extra functionalities, was having the stagnant light or the blinking light, and having an LED indicator for the battery status.